Okay, so my talk is, not not likely quite as entertaining as Vitali's this morning, Vitali's talks this morning, but hopefully not too heavy, and maybe you'll learn something interesting. All right, so this talk is on sort of algorithms, differentially private algorithms for convex optimization problems. When we're doing statistics and machine learning, often the sort of computational heart of the problem you want to solve is some sort of optimization. So, for example, I don't know, if you're solving the median, or if you're doing what's called ordinary least squares linear regression, or logistic regression, or perhaps fitting something called a support vector machine. These are all things people do in learning and statistics, and in all these cases, what you're doing, you're trying to compute some vector of parameters that best fits a data set in some sense, and then the natural way to do that is to minimize some sort of convex loss function. Okay. So these computations come up a lot in various aspects of statistics, and what we'll be talking about is sort of algorithms for solving these types of problems, right? So we've got you set up some loss function that depends on the data, and then you try and find some vector of parameters that minimizes this loss function. Okay, so I'll try to set it up a little more formally. We've got a data set that's a sequence of points in some universe U. And our goal is to find a parameter that minimizes some loss function. And the sort of important thing from the point of view of privacy is we're going to be looking at situations where the loss function is a sum of terms, and there's exactly one term for each point in the data set. And the reason this structure is helpful is it makes it easier to think about what happens, say, when one data point changes. Okay, and as I said, all the examples I gave before sort of satisfy this type of structure. Okay, so here the assumption we're going to make is that the loss function we're minimizing is convex is convex for every possible value x of a data point. And what convex means is that the loss function looks nice like this blue curve, right? So technically, convexity means that if you were to take the first order, for any point on this graph, you can find a linear function which is a lower bound for the function everywhere. Like if you were to take, say, the linear function given by the gradient, that's some sort of linear approximation to the graph in the neighborhood of a point, and the function is convex if that linear approximation is always a lower bound for the function. So it looks like this. And the nice thing about convex functions is that they have a well-defined minimum. Either the minimum is unique, or the set of minima is like itself a convex set, meaning they're all sort of nicely packed together. The other reason convexity is nice is because a lot is known about how to optimize them, and maybe we'll see a little bit about why that is. Like what is the role of convexity in the sort of why is it that convexity makes optimization easier? Okay, and the other assumption we'll make is that we're trying to optimize. We're optimizing over some set of possible parameter vectors, and that set is also a convex set. So in this case, we're trying to find. We've got some restricted range of values for theta, and on the line, a set is convex if it's just connected. And in higher dimensions, a set is convex if, for any 2 points in the set, the straight line segment that connects them remains within the set. Okay, so our goal is going to be to solve these problems without, as well as possible. And what does as well as possible mean? So let's recall that differentially private algorithms can't be deterministic. And so, in particular, you're not going to be able to return the exact optimizer in general for this convex function. You're going to have to produce an approximation. And so the notion of approximation we're going to use is called just excess risk, and it's pretty natural. It's sort of how much worse is the thing we output than the true minimizer as measured by the actual increase in the loss function. Okay? So this is slightly different in general from asking that theta hat be close to theta star. In some cases it implies that, but it need not in general. If the loss function is very flat, you could have a theta hat that's like really far from theta star but still pretty good. So this is the kind of quantity we're going to care about. And again, in the context of statistical computations and machine learning, this is sort of generally what matters. Okay. So here are some examples of convex loss functions, specific convex loss functions that really come up. So suppose I'm trying to find the median of a data set. Okay, so if I've got data arranged in a line and I want to find the median data point, well, of course, one way to define the median is to imagine the data set is sorted and you take the point that's in the middle. It's got n over 2 points to the left and n over 2 points to the right. But sort of a slightly more general way to define the median that makes approximation more, that helps us define approximation is to recall that the median is also the point that minimizes the sum of the distances to the actual data points. Okay. And that also gives us a nice generalization in higher dimensions. So in 2 dimensions, you imagine a sort of a bunch of points scattered around like on a table. And my median is going to be like a place where I can put my finger that minimizes the sum of the distances to the to those points on the table. As a physical interpretation with strings and weights and stuff like that, if you care about that, whatever. All right, linear regression is another example. This is sort of like high school linear regression. You're trying to find a line that approximates some scatter plot as nicely as possible. So your data set are given by pairs, where xi is a vector and yi is a single real number. And we're trying to find a linear function of the xi's that predicts the yi's as well as possible, as measured by the sum of the squares of the differences between yi and the predicted value xi dot theta. Okay, logistic regression is yet another example where the loss function looks a little different, but it's also convex. And support vector machines are yet another example. In that case, the loss function is sort of pretty easy to explain. It's given by, roughly speaking, the yi's are pluses or +1 or -1, and then the thing we care about is whether or not the sign of the inner product is the same as yi, and this is measured by some sort of absolute value function, absolute value-like function that again is convex. Okay, so these are all examples of the sort of general problem we want to solve. Okay. So why maybe just to help us sort of think through things a little bit, why is it that privacy isn't even an issue in this type of problem? So by the way, ERM, I forgot to define it, means empirical risk minimization. I'll actually sort of define this again, but anyway, it just means minimizing that excess risk that we were talking about a second ago. So in the case of the median, why is it that I wouldn't want to release the exact median? Well, if I write out the loss function of the related to the median, the exact minimizer, the true median, is always itself a data point, at least when the number of data points in the data set is odd. And so you're basically releasing somebody's data in the clear in this case, right? Somebody's income or somebody's whatever it is. This in higher dimensions the problems are sort of get a little more serious. Or for example, in the support vector machine, the standard way to encode the solution, the exact solution to this support vector machine optimization problem, is in what's called the dual form. And the dual form basically describes the solution of the this program that I described in terms of actual data points. So it's actually sort of like described as a specific linear combination of 3, in this case 3, or in general d+1 data points. And so again, the sort of solution of this very complex optimization problem is like just a collection of people's actual data, like in the clear. So we do need to think about privacy in these settings. And also, membership inference, right? So remember, Vitaly's talk this morning motivated that beautifully, but let me just, hammer home the point that in these problems, this vector of parameters that you want to output tells you a huge amount about, points in the data, and in particular, it's very easy to use the outputs of these types of optimization problems to test if a particular person is in the data set. And John will talk about that tomorrow. Okay, so again, here's the problem we're trying to solve. We've got this sort of convex optimization problem we want to solve. Our goals are going to be, we're going to try and find an algorithm A that's epsilon differentially private, and that outputs an estimator theta hat with small expected excess risk, or we might want high probability bounds on the excess risk, but for this talk, the difference isn't going to matter. There's a subtle point that I want to clarify, and then I'll ignore it for the rest of the talk. Is that really they're actually, when people are solving these optimization problems, they're really two kind of different but related problems they're trying to solve more or less simultaneously. So on one hand, sort of as described, what I said is we want to minimize this loss function that's dependent on the data. Okay, this thing is called the empirical risk function. But in fact, sort of more generally, what we really want to minimize usually is some sort of notion of population risk. So generally, the data will be drawn from some underlying population, and what I want to minimize is not the risk on the data set I have, but the sort of expected risk on a fresh random draw from the population. Okay, very much along the lines of what Kobe defined earlier. And these things need not be the same in general, right? So here the expected risk is the dotted line, and the empirical risk is the blue line. And when we take one sample, we get one version of the expected risk of the empirical risk, and in the other version we get a different version of the empirical risk. Okay, so so really there are two separate goals. You could either ask to minimize the empirical risk or ask to minimize the population risk, and it actually turns out that the results you get are actually slightly different in these two settings. There really is a noticeable difference between the two. Sorry, that's not what I wanted to say first, but I'll skip over it. But nevertheless, in general, the difference between the two is bounded for differentially private algorithms. So as Kobe actually proved in his talk this morning, in general, the difference between the empirical risk and the population risk is going to be bounded by epsilon plus delta for an algorithm that's epsilon delta differentially private. And so actually for the remainder of the talk, I'm going to focus exclusively on empirical risk. The exact bounds we get on accuracy are going to depend on various properties of the specific problem we have at hand. They're going to depend on various properties of the loss function L, like for example how smooth or nicely curved it is, various properties of the convex function, this convex set over which we're optimizing, like whether it's round or has sharp corners, various assumptions about the expected risk, this R function. And I'm going to sweep a lot of that stuff under the rug, and what I'm going to focus on are the different techniques people use the different algorithmic techniques people are going to use. I'm not going to spend a lot of time on how exactly we analyze privacy or utility in these settings. But a nice representative setting is where a function is what's called one Lipschitz. And I'll define exactly what that means in a second. The functions we care about are Lipschitz. It's sort of a measure of smoothness. And the other thing is where that the convex set we're optimizing over has bounded diameter. It lives, let's say, within the set of real vectors that have Euclidean norm at most 1. So just to sort of nail down this Lipschitz assumption a little more precisely, so the reason we're going to make this Lipschitz assumption is to bound how much any one person actually influences the output of the optimization problem we care about. So if any one term in this sum can be kind of arbitrarily huge, then one person can totally screw up the problem, and there's no meaningful way in which we're going to be able to provide differential privacy, at least without throwing out data points or things like that and changing the definition of the problem. So in order to make things clean, we're going to limit how much any one person's data influences the optimization problem. And the way we'll do that is by assuming that each of these little loss functions is what's called Lipschitz. And like just a very concrete way to think about that is to assume that the gradient of the function, that is the vector of partial derivatives, is like not too big. It's just, it has bounded Euclidean norm. Let's call it bounded by a constant C. For all possible data points and all vectors in the convex set C. Okay, and this is basically some measure of smoothness, right? So we're it just says this little loss function doesn't change too quickly as you move theta back and forth. Okay, so under these assumptions, we actually have like a pretty good understanding of how low we can get the empirical risk for these types of problems. So for example, under epsilon 0 differential privacy, the empirical risk is as low as d over epsilon n, and that's tight in general, even for very simple functions. Under epsilon delta differential privacy, we can sort of shave off an additional square root of d. Here d is the dimension of the parameter vector theta. These results are tight, and they're tight they're tight by virtue of a set of arguments called tracing attacks or fingerprinting lower bounds that John Ullman will talk about tomorrow. And I'll explain the algorithms that achieve these bounds. I won't actually prove why they achieve them, but I'll explain like how they work. And then just to sort of give you a little bit of a flavor, when you start making extra, when you're in settings where the loss functions you care about satisfy extra assumptions, you can make stronger statements. So like a nice property that often holds, for example, for linear regression and related problems is what's called strong convexity. So in that case, that basically strong convexity, I won't define it super formally yet. It just means that the function is sort of nicely curved. It doesn't have flat parts. And then suddenly, like under the assumption of strong convexity, you basically make the error goes down much faster. It actually roughly squares the optimal error. So instead of being d over n, it's like d squared over n. And instead of being square root of d over n for epsilon delta, it's like d over n squared. Okay, so I guess the message of this slide is both that we sort of have a pretty good understanding of how well we can solve these problems in a number of settings, and secondly, that the more you know about the structure of the functions you're optimizing, very often the more you can say, the more sort of you can tailor the algorithms to the problem, which is maybe not so surprising. John will talk about lower bounds tomorrow, so I'm not going to say anything more about that. Okay, so at this point, there was this original paper, actually a pair of papers that appeared, they didn't appear the same year, but they actually came out right at the same time, by Kamalika Chowdhury and Claire Monteloni, one paper, and the other by Ben Rubenstein, Peter Bartlett, someone, that's probably what the S stands for. It's not me. It's some other person whose last name is S, and Nina Taft. And both these papers kind of posed this problem at some fairly high level of generality and gave initial algorithms. And then there's been this sort of slate of other work proposing different algorithmic approaches and different results under different assumptions and all that. And again, what I'm going to do is try and outline just the sort of algorithmic ideas that go into these results and not the sort of exact analyses. Okay, so let's start with output perturbation. And for output perturbation, we will actually be able to prove, top to bottom how well it does. So, so for output perturbation, as I said, we are gonna need an extra assumption. So we say that a loss function is a convex loss function is lambda strongly convex if it satisfies this equation. And what that really means is that not only is the loss function, sort of lower bounded at every point by a linear approximation to the function, but actually it's lower bounded at every point by a quadratic approximation to the function. Okay. And so that means, in particular, there are no flat sections of the function. It always has curvature, at least lambda is sort of measured in this way. And this lambda is some measure of just how curved it is. So it tells you that it's just a coefficient in front of the quadratic part of this approximation. Yeah?
Are there fixed x's in here?
X's?
So like the data?
Oh, so what we need is that for every data set, the big loss function, or actually you don't, well, yeah, let's say simplest version is for every data set, the big loss function is a lambda strongly convex. So it's not so much a property of an individual data point as the sum of all these things. And there are a couple of ways to enforce this condition by like adding terms to the loss function, but let's just say we have it for free. Like for example, for linear regression problems, you get strong. It's just the loss function is always has this kind of property. What is F? Good question. F is L. I'm sorry. Yeah. Thank you. I didn't I guess I must have made this. Yeah. Must have changed notation at some point and not propagated the change. I'm sorry. Okay, so when L satisfies this additional strong convexity assumption, there's a nice simple algorithm that we can do, and it's actually an algorithm we've seen a bunch of times in this winter school so far. So what we're going to do is we're simply going to add noise, random noise to each component of the output. Okay, so we're going to compute the true minimizer of our big loss function L, and then we'll just add some noise to that and release that noisy thing. Okay, and the question is, why can we do this? How much noise can we add? And the answer is, well, it depends on this lambda property and the sort of how smooth the function is. But the amount of noise we add, in order to sort of add noise in this way, we said you need to have some bound on the stability of the function you want to compute. And in order to bound the stability here, we can use the following lemma, which is a very useful thing to know if you play with convex functions at all. And it's the following thing. If L is a lambda strongly convex function, and little f, not the same little f as above, that was really L, but this is a different function, is some little function that is itself C Lipschitz, meaning smooth. And then what we can say is that under these conditions, the minimizer of if I add think of this as adding a new person to the data set. If I add a new person to the data set, I'll get some new loss function L plus F. And if I can compare this to the optimizer of the original function L. And what I want to say is that the distance between these two is not very big. Okay, so for any loss function L that's lambda strongly convex, and any perturbation I add to it that's C Lipschitz, the difference between the amount by which the minimizer can move is at most C over lambda. Okay, and in these in the setting of privacy, because I'm actually averaging people's loss functions, this C is going to be on the order of 1 over n, and lambda is going to be on the order of a constant. And so what I'm going to get is that adding any one person to the data set is going to move the optimizer by the minimizer by a distance of at most order of 1 over n. Okay, and so then I can add about this much noise to each component of the loss function, and I'll satisfy differential privacy. So let's just to give you a sense of what's going on, let's just prove this strong convexity lemma. So yeah. No, f is going to be, so, okay, so we want to add noise to the true minimizer. So what we need to understand is how much would adding one person's data move the minimizer? How much can it possibly move the minimizer? And I also want you to understand why it is that this sort of smoothness assumption actually plays a role, and it is basically because of this lemma. And what we're saying is that when you add this little perturbation f, so think of that as like 1 over n times this new person's data, then we move the minimizer by, in this case, 1 over n divided by some constant lambda, and so the sort of total distance that the minimizer can be pushed is on the order of 1 over n. Okay, so so let's just prove this. Okay, so we've got two minimizers, theta 0 and theta 1. Sorry, I changed notation. And delta is the magnitude of the difference between the two, and this is the thing we want to bound. Okay. And so, sorry. By strong convexity, what do we know? We know that the blue function is bounded below by some quadratic function that's sort of centered at theta 0. Because theta 0 is a minimizer, the linear part, the gradient at theta 0 is 0. And so the quadratic function is just like a simple quadratic function. It has no linear term, centered at theta 0. And so what I can say is that the difference between the loss at theta 1 and the original loss at theta 0 is actually pretty big. It's at least lambda times delta squared. Okay, so that tells you that if I push theta 1 very far away, if theta 1 were very far away, then the blue function would actually be really big at that point. Okay. But on the other hand, we also have smoothness of the difference function. So let's get an upper bound on this difference. So so we know that the loss of the difference between L at theta 1 and L at theta 0 can be bounded by simply adding the difference between L plus F at theta 0 and L plus F at theta 1. So that's a positive, L plus F is bigger at theta 0 than at theta 1, so I'm getting an upper bound by adding that difference to the difference I care about. And now there's like a bunch of stuff that cancels. So L of theta 1, minus L of theta 1 goes away, minus L of theta 0 plus L of theta 0 goes away. And what I'm left is just the difference in F at theta 0 minus the value of F, little f at theta 1. Remember, little f is like the small function, the little perturbation. And by definition, it's at most, because it's Lipschitz, it's at most c, sorry, there's an extra f that got thrown in there, but it's at most c times the length of this, the magnitude of this perturbation. Okay, so I've got an upper bound and a lower bound on how much the blue function L changed, and just by by comparing them, by saying, well, lambda over 2 delta squared is less than c times delta, then I get that delta is at most 2c over lambda. And that's it. Okay. So again, the reason that I can sort of bound the amount by which the minimizer moved is because I know this perturbation function f doesn't change very quickly, and so f of theta minus f of theta 1 can't be very big. Okay, so that's it. And this is a very simple lemma, but I don't know, it's somehow emblematic of the kind of analysis that goes on when we're thinking about these types of problems. Okay, so what's our full algorithm? We'll pick a random vector. I chose to use the Gaussian noise, but you can use other distributions. Basically what we're going to do is, suppose we've got some function we want to minimize. Either it's already strongly convex, in which case we don't need to do anything, or it's not, in which case we can add a quadratic term to the loss function, which will make it strongly convex. And then we add this. Whoa, sorry. Let me. Sorry, that was a different slide. I was explaining something else. So let me stop here. Sorry, not stop here, but like go back. So we said we were proving this convex stability lemma. What does that allow us to do? It tells us the amount of noise we need to add to get this to the minimizer to get differential privacy, and then the amount of error this will induce in the final solution is will depend on the loss function. But basically, because the loss function itself is reasonably smooth, you can say that this noise doesn't mess things up too much. Okay, so that's all I wanted to say about output perturbation. Now I wanted to move to a different technique. Sorry, I was like got my slides mixed up. Yeah.
So this technique is for the case when I observe the output of the trained model, and the output is private.
Yeah. So in all these settings, for all the algorithms that we're going to discuss, what I want to do is output the parameters of a trained model. Okay, so that is sort of everything I'm going to discuss in this talk. That is the way it looks. You can also ask what would I have to do if all I wanted to output were sort of predictions on maybe some new data points and something. And there is sort of there are some interesting things to be said about that. But maybe a good lesson to learn from Vitali's talk is that actually if your model leaks information, there's a reasonable chance that its predictions are going to leak information. And so this is sort of a much safer way to think about it, right? Okay, so let me explain a different technique now. Sorry for the confusion. This is a technique called objective perturbation. It's due to Chowdhury and Montoloni and Sarwate in 2011. And it's sort of a repaired version of some earlier idea that wasn't working properly. But here the idea is going to be rather than sort of computing an exact minimizer and then adding noise to the minimizer, what we're going to do is just add noise to the loss function itself the loss function we want to change. And the way we're going to do this is we're going to pick a random vector, and we're going to add a linear term b dot theta, random vector b, we're going to add a linear term b dot theta to our loss function L. Okay? And then what we're going to do is we're going to minimize this, this sort of perturbed loss function. And it turns out that for technical reasons I'm not going to be able to explain, that we're going to also want to add an extra term to make sure this loss function is very slightly strongly convex. But this lambda here is going to be pretty small. It's going to be on the order of 1 over n. So it's sort of this term here actually doesn't really change things very much. It just it basically makes the minimizer well defined. That's essentially the role it plays. And now, so what we're going to do is we're going to, another way of thinking about this is that we're going to try to, rather than setting the gradient to 0, which is normally how you'd try to minimize a convex function, we're going to set the gradient to be this random vector b, plus this extra little term that comes from the strongly convex, what's called a regularizer. Okay. And so it's kind of like, rather than finding the point where the dotted red line is flat, we're going to look for a point where the linear approximation is given by this, the slope of the linear approximation is given by this vector b. Okay. Alternatively, you can imagine as sort of looking at the loss function, tilting your head, and then like minimizing the resulting thing. Okay, so it turns out that this algorithm is differentially private as long as the loss function is as long as the loss function is what's called smooth. So it turns out smoothness is a little stronger than that Lipschitz condition I defined earlier. It also requires that the gradient not only the gradient not be very big, but that it not change quickly. And it really doesn't work if you don't have these additional assumptions. So for example, it doesn't work for the median problem, which has a bunch of like sharp corners in the loss function. So that's a non-smooth loss function, and you won't get something differentially private. But as long as you stay away from those loss functions, it works nicely. And you can add extra, it works, there are some convex problems where you actually want to add an extra penalty term that's not data dependent. That extra penalty term can be non-smooth. So for example, that's what happens with a common common algorithm called the lasso algorithm. Okay, so this is actually a fairly applicable method, and the intuition is very clear for what's going on. So again, rather than adding noise to the output, we're just going to perturb the loss function itself a little bit, and then minimize the perturbed loss function. Okay, when it applies, when the loss function is smooth, this technique is generally much better than output perturbation. But it's limited by the fact that it doesn't apply to all the problems we'd like it to apply to. It doesn't apply to the median, doesn't apply to training support vector machines, and to a number of other similar optimization problems where the loss function has like sharp corners in it. Yeah.
How did you derive the amplitude of the noise that you
Right.
by GMO?
Right. Let me sort of give you a. Right. Okay. So let me give you an idea. So let's see. It comes out of the. I'm trying to see if I can give like a short explanation that won't take a while, but I don't think I can. So okay, I think it'll be too long a digression. Right. The way you analyze privacy here is by looking at this sort of equation that's defined implicitly by your optimization function, by the optimization problem you're solving, and that sort of defines a distribution on theta hat. You want to know how does the distribution change, and basically by using calculus, you can figure out what the density function at this point actually looks like, and you can actually compare two density functions basically explicitly using like the implicit function theorem for implicit derivation. So, I don't know of a kind of a short, clean way to explain it without doing all the calculations, but I'm happy to explain it offline. Okay, so this is another algorithmic technique, and again, it's very natural. So I should say a good feature of both this technique and the previous technique is that if you've got software already written for solving these types of optimization problems, you can just use it. Okay. Whereas from now on, we're going to start like running into techniques where we're actually going to, if we're sort of interested in implementing these things, you actually have to write the software yourself from scratch. And that means like coming up with, say, optimized version, things that run really fast is going to be a lot more work because you can't just sort of leverage existing packages as simply as you'd like to. Yeah, in order. Yeah. Right. So I didn't. Yeah, there's this term up here that what really matters is the diameter. So actually, what really matters is the diameter of C. And yeah, I didn't actually say that, but this is going to be like what you're going to do is take the set over which you're optimizing it and move it, translate it so the center of the origin is in the set. Right. So otherwise you're absolutely correct. Yeah, there was another question.
Yeah, I'm trying to think of adding something to the loss function.
Mm-hmm. That's the idea, yeah.
It reminds me of the surrogate loss.
Yeah, you can think of it as a surrogate loss. You can think of it as Bayesian inference with a random prior. Right? Which is like a weird way to think about it, but technically it matches. You could also, what's sort of maybe more natural is that in certain problems, depending on the structure of the loss function, you can think about it as adding a small number of random people to the data set and then optimizing. Okay, so like for linear loss functions in particular, this sort of has that interpretation. Yeah.
If I'm using a surrogate
Well, okay, so the way I've defined this, I'm not sort of making any assumption about what this loss is other than, convexity and stuff. In particular, I'm not saying that, this loss is just whatever you've decided you want to optimize. So if you're going to optimize some, other loss function other than the one that's natural for, the probabilistic model you have in your mind, then that's what goes there. Right? So I'm not assuming that this loss L somehow corresponds to some true probability model or anything like that. Okay, so in particular, say for techniques like the lasso, you pose what you do is there's some non-convex problem you want to solve, you pose a convex version of it, solve that instead. What goes here is the convexification of the original problem and not the original one. Okay, so let's look at another another version of this problem inspired by the exponential mechanism. Well, it's actually a special case of the exponential mechanism that that Katrina defined in her talk Monday morning. So here we're going to so this is yet another technique. Okay, so what we're going to do is rather than sort of explicitly optimizing the loss function, we're going to sample from some probability distribution that puts a lot of weight on good solutions to the problem. And specifically what we're going to do is we're going to define a probability distribution. We're going to start with some prior distribution on the convex set C. That could be the uniform distribution. That's sort of the simplest case, but you could plug something else in if it makes sense. And then what you're going to do is you're going to reweight parameter vectors according to the loss function by assigning high weight to things with low loss and low weight to things with high loss. And you're going to increase this penalty exponentially with the loss. Okay, so this defines a density function on the convex set. And basically on input x, what you do is you output a sample theta hat just drawn from this distribution. Okay. Now, under the assumptions I made before about Lipschitzness and boundedness of C, this loss function big L, it has sensitivity 1 over n at every point theta. That is, for every value of theta, if I change a person in the data set, the value of L changes by 1 over n. Okay? And so this specific penalty term here is exactly just a special case of this exponential mechanism, except the way Katrina defined it, she was optimizing over a finite set. Here we're optimizing over an infinite set. So one question that's sort of maybe not totally obvious is does there always exist a probability distribution that is whose density function is proportional to this weird function? And it just turns out it does. It's bounded and on a convex set, so that's not going to be an issue. In fact, this is the type of distribution you get out of this process is what's called a log concave distribution. And so there are nice algorithms for sampling from these log concave distributions. Okay. You have to be a little careful that you're really sampling from the exact distribution, not some approximation to it, but it turns out, and then there's work to be done to think about whether or not you're really doing that, but let's pretend that issue can be resolved. Okay. And then it turns out that we can analyze so this process will be differentially private simply by virtue of it being a special case of the exponential mechanism, and then you can analyze, you can show that this argument, that this process is a good one. You can analyze utility via some sort of something we called a peeling argument in the paper where we did this, and you're essentially sort of dividing the convex set over which you're optimizing into sort of a discrete set of subregions corresponding to the level sets of the original loss function lambda L, sorry, and then basically showing that the regions where the loss function is low have high mass. So it's a kind of more involved version of the utility argument that Katrina presented on Monday morning. And I'm not going to go through it in detail. I just want to sort of give you a flavor of what's going on.
Adam?
Yeah.
Is the fact that you are approximating the log concave distribution, is that an issue for Python?
It is, actually. So I didn't want to go into it, but you have to make sure that, so either you have to be sampling exactly from this log concave distribution, or you have to make sure that the distribution you're sampling from is sort of epsilon close to the correct one in the usual in the usual notion of, like, according to epsilon zero differential privacy. So there are a couple of ways. You can either get epsilon delta by just sort of sampling from something statistically close to the true distribution, or what we did in the paper is you can work like much harder to make sure you're actually preserving epsilon zero differential privacy. Yeah, just by running. I guess. Yeah, I'll take a minute to say. So the way one normally samples from these log concave distributions is by running some kind of Markov chain on the convex set. Like a very simple one is you sort of pick a random direction and focus, like you've got some point that starts off somewhere and it's going to proceed by taking a bunch of steps. And essentially the way it works is you sort of pick a random direction and then sample from the one-dimensional distribution defined by the line you live on in that direction. And you just repeat that a bunch of times. It's called a hit-and-run sampler, and it works pretty well in this setting. And there are other similar mechanisms. And so what you can prove is that if you run it long enough, it'll converge exponentially quickly in statistical difference to the correct thing. So you can basically make your delta as small as you want, and it doesn't have any effect on accuracy. It only affects running time. Okay, so another algorithmic technique that actually also sort of achieves very good utility, both in practice and sort of in theory, is some kind of noisy stochastic gradient descent. So you're going to run an algorithm. We're going to run an algorithm that is sort of well studied in the optimization literature called stochastic projected gradient descent. And but then we're going to run a noisy version of it. Okay. So normally the way gradient descent algorithms work is you start with some point for optimization. You start with some point. You measure the gradient of your loss function at that point, and you take a step in that direction. Okay. Stochastic gradient descent is one where rather than sorry, I need to make sure my battery doesn't die. Okay. For stochastic gradient descent, what you do is rather than fully, computing this full gradient, which is, can be expensive to compute because it's a sum of n terms, one for each term in your data point, you just pick one random data set, one random point from your data set, compute the gradient at that data point, and pretend that's your real gradient. Okay? So that's a technique called stochastic gradient descent. And the reason it works is because at least in expectation you're getting the right thing, even though on any given iteration you might not be getting the right thing. And so the noisy version of that is you're going to pick a random point in your data set, you're going to compute its gradient, you'll add noise to that gradient, and then use that noise use that noisy gradient to sort of take a step hopefully towards the minimizer. And the way you do this is you take you've got some parameter vector that you're maintaining, you subtract off this noisy gradient, and then if it happens to take you outside of the set C, you project back into where you were. Okay, so this sort of idea, it's obviously fairly simple. It actually works remarkably well. There are various variants on it that were evaluated empirically. In some starting with this paper of Ollie Williams and Frank McSherry, and then we gave some improvements to it and a much tighter analysis that allowed us to get like nice clean theoretical bounds in a paper with Raif Basili and Abradeep Thakurta. And actually, sort of one of the cool things that came out recently is that this idea was used to give a differentially private algorithm for deep learning. So deep learning is cool because everybody does it. And in this paper written by a bunch of people at Google, what they showed is that this same idea could be used not just for convex problems, but for this very non-convex problem of fitting the parameters of a neural network. And they also gave like a much tighter privacy analysis than we gave. It doesn't change the asymptotics, but they have like a very careful accounting of the privacy loss as they run this algorithm. And it's sort of a nice study in like how to pay really, really careful attention to kind of what's actually going on in the algorithm. That's a nice paper to look at. I wouldn't be surprised if there are improvements to be made to that paper. We'll see how the state of the art evolves. Okay, and maybe one feature of this, the analysis of these types of algorithms is it turns out you can take advantage for privacy of the fact that you're only sampling one data point at each step, rather than the fact that you can take advantage of the fact that you don't publicly output the label of the data point you're using to estimate your gradient at each step, and that allows you to get like a very clean privacy analysis. Okay, so I had some pictures for how it works, but I'm going to skip. Yeah.
Isn't it actually supposed to be worse in terms of privacy, the fact that you're just using one example in order to calculate the gradient?
Well, sort of, it's a trade-off. So it turns out that sort of, yeah, so there's something going on. There are like a couple of things going on here. So when you just pick one point, suddenly your gradient is much more sensitive, right? However, so you have to add like a fair amount of noise, okay, to the gradient. However, the trade-off is because you're using only one point, you can show that you actually end up leaking way less information, way less. There's this kind of amplification effect where if you've got an algorithm that, let's say, is 0.5 differentially private, and you run it on just one random point rather than all n of your points, the resulting process is actually going to be 0.5 over n differentially private. Not exactly 0.5, but like it's kind of 0.9 over n differentially private. And so there's this kind of trade-off, but basically these two effects balance out. On one hand, the sensitivity goes up. On the other hand, your privacy loss goes down, and they balance out. And what you get is like a very similar to what you would get just by evaluating the whole gradient and adding noise to it, but computationally it's much simpler and more efficient. Okay, and basically this process I just suggested, where you sort of pick a random data point or maybe a small subset of random data points and evaluate the gradient on those points and add noise to it, it's not useful only for gradient descent. It's actually useful for sort of any algorithm that expects that works by making a sequence of gradient queries to your loss function. And it turns out there's this whole family of well-studied algorithms in optimization that do this, called first-order methods. First order because they're looking at the gradient and not higher-order derivatives. And sort of variations on that have been studied to give better differentially private algorithms for optimization over other convex sets. So not when you're optimized not over say the unit ball, but like other sets, and in particular over polytopes, it works really well. So there's something called the Frank-Wolf algorithm that is sort of a variant on gradient descent, but where your update rule works a little differently. And there's this sort of nice paper of Talwar, Thakurta, and Zhang, where they show that you can give like a differentially private version of this that works well in very high dimensions. And specifically what they're doing is they're using like, rather than actually explicitly evaluating the gradient and adding noise, what they're doing at each step is sort of, you're optimizing over some polytope, and they're using the exponential mechanism to select a polytope, a vertex of your polytope, that optimizes the vertex you would get to if you tried to optimize in the direction of the gradient, because that's sort of how Frank-Wolf works. Okay, and basically they observed that just because of the specific structure of the Frank-Wolf algorithm, you can get away with using the exponential mechanism instead of noise addition, and it gives you this sort of much, much better dependency on the dimension for certain classes of optimization problems. Okay. I'm running out of problem. Another sort of direction people have taken in the research, in the literature, is to look rather than trying to solve just a single problem, they look at what happens when I have, in fact, a sequence of optimization problems to solve based on the same data set. Okay. So there are various reasons why this might come up, but in particular, maybe I'm trying to fit a bunch of different models to decide which one is the best, or to answer a variety of different questions. And in that case, one thing we could do is to just solve each of the models in the sequence differentially privately, fit each of the models differentially privately, and that would work. Except then, by the composition theorem, the error we're going to incur is going to increase at a rate of about square root of k as we solve this kind of a sequence of problems of length k. And what John Ullman in this sort of 2015 paper showed was that you could actually do better by, roughly speaking, by reusing information across this sequence. You can view these first-order algorithms that make gradient queries as making asking a sequence of linear measurements, and then you can use this private multiplicative weights algorithm that he actually described the other day, yesterday, and yesterday, whenever it was, to kind of keep track of the information you've learned along the way and get improvements in the privacy analysis by sort of combining this sequence of models. Okay, and when the universe in which your data points live isn't very big, you get a much better dependence on k. So rather than going up as square root of k, it goes up as log k. And when I say the universe isn't very big, I mean it's like not too large an exponential in n. So it can be pretty big, but not too big relative to n. Not too exponential relative to n. Okay, so it's still logarithmic in the size of the universe. Okay, in particular, this is if for kernel learning methods, if you know what that is, this is like a good family of algorithms to think about. I have a slide on differential privacy and generalization error, but you know that from Kobe's talk. Basically, solving these empirical risk problems also helps us solve the population risk problem that normally is the problem we're really trying to solve. And that's just via a generic connection between differential privacy and generalization error. Okay, so there's like a lot of work on private optimization that I didn't talk about, so I just gave you kind of a flavor of some of the different things that are done. There's lots of work on online learning, a number of papers, nice papers on using random projections to, I don't have all the citations on the slide, but a number of papers on using random projections to sort of compress the data to a more compact representation, which has some benefits for privacy. There are a whole pile of papers that I can't even hope to cite on designing like algorithms that are highly tailored for very specific optimization problems. And there's a number of works on optimization in the local differentially private model that I talked about yesterday. And there's other stuff, other works out there that I'm sure I don't have on the slide. By the way, I have at the end of the talk, at the end of the slide deck, I have a bunch of references to all these papers I'm mentioning, in case you want to read more about it. One thing I'll just mention about the local model that is that's not an issue in the central model. So when we look at these first order methods, they involve you kind of going back and forth to the data, right? You sort of compute some gradient, update your parameter, compute something else on the data, update your parameter, and so on and so forth. When all your data live in one place, that's not a problem, right? That's just reading the data. But In the local model, where your data are distributed across devices, so maybe where each data point lives on someone's iPhone or smartphone, then the sort of state-of-the-art optimization techniques will tell you to do is to use gradient descent in the following way. I'll sort of send a parameter to the first person and get back a noisy gradient at this first point, and then I'll update my parameter, send the updated parameter to the second person, and get back a noisy version of my gradient, and so forth. Theta up to theta n, and I'll do this in order to get the optimal error. I actually have to do this n times. I have to go back and forth n times. Okay. And in any kind of real implementation, this sort of very sequential nature of the interaction is a serious problem, because basically it means that this aggregator that's talking to all these people has to be online during the entire execution of the algorithm, and also there's a timing issue that any latency in the network makes the whole thing take just a long time, right? So there's actually an open question, which is whether or not one can achieve the optimal error for natural optimization problems in this setting completely sort of non-interactively, with just messages going, maybe one broadcast message from the aggregator to everybody saying we're going to start the protocol now, and then a message from everybody to the aggregator with some information, and then the aggregator just does the computations offline. Okay? There's no reason to think one cannot do this, but none of the algorithms that are known have this property. So there's an interesting open question there. So if you're interested in sort of optimization and learning and these types of things, this is something that I'm told people at Apple and Google and places like that actually care about. So wrapping up, the state of the art is there are a variety of algorithmic techniques and also nice impossibility results for private optimization and the line I've been talking about. Under some fairly general conditions, we know worst case bounds, tight upper and lower bounds on the empirical risk we can achieve, but in general, we don't really know how the structure of the problem helps us. We have some examples of how you can take advantage of extra structure in the problem. For example, various geometric aspects of the set of constraints or extra properties of the function, but we don't have a full understanding by any means. And also another thing I didn't get into the level of detail to specify is that there's some open problems on the exact generalization error bounds. So as I said, we sort of understand the empirical risk bounds a little better than the generalization error bounds. And finally, there are some nice connections here between computational efficiency and privacy, meaning the reason a lot of these algorithms work and provide privacy is because they're based on sort of non-private algorithms, say gradient descent, that don't need to know too much about the loss function in order to optimize it. And there's a strong connection, for example, between how many rounds how many times the non-private method needs to query the loss function, and how much privacy you lose as you go, and how accurately you can do things differentially privately. And so that connection is interesting, and again, not totally fully understood. And then the last thing I'll mention that I mentioned earlier is that a lot of the techniques developed in this convex case, where we can actually analyze things and we can prove nice theorems and stuff like that, have also been used for non-convex problems, and they provide, the insights we learned in this sort of simpler setting transferred nicely to that more complex arena. Okay, so I'll stop there. Thanks.